All right, so some of the things that we're going to do, guys, are the things that we've been doing. It might not be until 2 weeks from now, 3 weeks from now, 4 weeks from now that you kind of realize and we look back and say, oh, now I understand why we did 2-2 by itself and looked at these if-then statements by themselves. And now it also makes sense that why that progressed to biconditionals and progressed into what we call today deductive reasoning, okay? So it's kind of that phrase that hindsight's 20/20, right? If I look back on something, I can understand maybe the reason why we did some of the things that we've done, okay? When we go through and do some proofs here in the next couple days and then throughout the next couple months, we're going to be using inside these proofs things from 2-2, and then things from 2-3, and things from 2-4. So I'm trying to kind of help you build the skills individually of those things so that when we kind of collectively smash them all together inside a proof, it makes it a little bit easier process to smash them all together inside a proof, okay? So that's going to bring us today to talk about deductive reasoning, all right? If I give you the list of numbers 2, 4, 6, 8, what's the next one? No, it's 13. How do you know? How do you know it's not true? If I give you, huh? Okay, so it's following a pattern, but who's to say that that's not, because you don't know what that next number is, who's to say that pattern doesn't change, right? And that's something we'll talk about when you get to Algebra 2 and advanced math with sequences and series. But you're absolutely right. A lot of you said 10, right? Because you're going off the pattern and saying that I think because of what's already happened, I know, or I think I know that this next thing's going to happen, okay? So I'm making a best guess kind of situation there, right? Okay? I'm thinking it's 10, but, you know, it could be maybe 13, okay, or any other number.
So isn't it like we divide out 7 by any number? Like 1, 4, 6, 7, and getting
I don't know what you're talking about. Keep that and share with me. But I guess what I'm saying here, guys, is when we talk about that idea, when you're going off what Riley said, she said pattern. There's a pattern. Absolutely. That's what I was looking for. Okay? When we do pattern-based arguments, it's called inductive reasoning. Okay? Inductive reasoning. And the argument that we make or the assumption that we make next might be true, might not be true. It just depends on what the next number really is. Okay? So if you ever make an argument based off of inductive reasoning, it's because you've been looking at patterns and using patterns. Okay? Seeing that this is the way it worked in this situation, it happened again in this situation, it happened again in this third situation. So this fourth situation, I think it's going to probably happen the same way. Okay? That's inductive reasoning. Okay? It's good. It's nice to have. It's something that we use in mathematics quite a bit, but there's a process to show that it's valid in mathematics. I want to kind of open your eyes to this idea in like a courtroom setting. Okay? Let's say Mike is being convicted of a crime. Okay? He's in a courtroom. He's got his lawyer. He's got the prosecutors there and everything like that. Let's say he stole a car. Okay? Or we think he stole a car. And the only evidence that we have on Mike is that somebody was at the scene of the crime, and they're able to tell me, you know, the guy that stole the car, he was a male. He had a ski mask on. He had baggy clothes on, and that's all I can tell you. Okay, but maybe I tell you his height and all that kind of stuff. Okay, or estimate his height. And Mike has that height. He's male. All right, so kind of not a very good case to say that he was the person that we're going to convict of this crime. Would you guys agree with that? Okay, say we go to court with this and all that kind of stuff. One of the things that they're going to do as a prosecutor or even a defendant is that they're going to bring in people that are called character witnesses, right? They're going to come up or talk to the jury, come up on the what do they call it?
podium.
What's it called? The pitch, yeah. Okay, and they're going to question this person and say, okay, you know, what kind of person is Mike? How long have you known him? Okay, has he ever shown like similar behavior? Like, is he a thief? Has he got previous records and stuff like that, criminal records against him. And basically what we're trying to do is lay out kind of a pattern type idea, right? Has he shown this behavior in the past? Because if he has, then maybe chances are we can maybe go a little bit further with this conviction and maybe come up with a valid kind of ruling. Okay, so yes, he did end up stealing his car or not. That's inductive reasoning. If you're in court and that inductive reasoning is happening to you, you better hope that you've got a pretty good lawyer that can kind of attack those character witnesses. Does that make sense? Okay. What we really want is what we call deductive reasoning. If I'm the prosecutor, okay, or if I'm Mike, okay, if I'm the defendant, I want to make sure that we've got facts. I've got DNA at the site or inside the car that matches Mike. Okay. I've got Mike on video surveillance, walking around, scoping out cars a couple days before this happened. Okay. I've got surveillance of Mike getting out of this car at some point later on in the day. Does that kind of make sense? Okay. I want facts that show that, yes, we can make the argument that he indeed did do this crime, right? That fact-based kind of conviction, that fact-based argument is called deductive reasoning, okay? And that's what we want to kind of focus on right now in this course, okay? We will do some inductive reasoning because usually inductive reasoning, or a little bit of that, and using that process for proofs is more algebraic than anything, okay? Deductive reasoning is going to be more based off of our definitions and our postulates and other theorems that we have, other statements, other if-then statements, okay? So deductive reasoning, by definition, is the process of reasoning logically, okay? So when I talk about reasoning, I'm just talking about thinking, right? Coming up with an argument, coming up with a progression of statements, okay? So it's the process of reasoning from given statements or facts to a conclusion, okay? And we want to make sure that if we're in a courtroom, that deductive reasoning process eliminates any gaps, okay? If you're convicted of a crime, you want a pretty good alibi, right? You want to make sure that your defense attorney can say that my client was not in the vicinity of this area or this crime during the time in which you said the crime occurred, okay? Because if we can do that, if we can make sure that there are no gaps there, that's great, okay? If we go back to Mike stealing the car, and let's say this car got stolen at 1:30, okay, and Mike can't come up with, and nobody can corroborate, what's that word, his whereabouts at 1:30 in the afternoon, that's a problem for Mike, right? Okay, that's a gap in his defense that, okay, a lot of things are going good for him in regards to that he didn't steal the car, but he can't tell us and nobody can verify where he was at 1:30 on the day that this thing occurred. That's a problem, right? When we do proofs mathematically, we don't want gaps or problems like that, okay? And we shouldn't if we go through a kind of a logical process that hopefully these intermediate sections of this chapter are going to kind of try to teach us, okay? It's the idea of making a conclusion based on already known facts. Okay, our definition, they are facts. Okay, they are things that the math community has said, this is how we're going to call this object. This is how we're going to categorize it. This is the characteristics that put it in that group. Definitions are kind of agreed upon facts. Okay, postulates, we've already talked about how those are agreed upon facts. Okay, and the last one are theorems. We haven't defined what a theorem is, but it's a fact. Okay. But a theorem is different than the other things. A theorem is something we can prove, okay? And essentially, the first theorem we come across is taking some definitions and taking some previously known postulates, and we piece them together, okay? Because they are true. The definition is true. The postulate is true. If you piece them together, it gets us a new statement, which we call a theorem, and it's true as well. And now we've got a first theorem. Then we do that again with maybe that theorem and a postulate, and now we get a second theorem. And we keep doing that. We collectively create a bigger group of theorems, okay, or statements that are true that we can prove to be true. Okay, so the Pythagorean theorem is one of those things, okay? The Pythagorean theorem takes a cluster of previously known information, previously known math information, and it piggybacks it off of one another, and it leads us to the argument that a squared plus b squared equals c squared all the time for right triangles, okay? So every time that we see something called a theorem, kind of this stuff is being used. It's what we call law of detachment, law of syllogism here in a moment. Okay? So the law of detachment, this is the first law. And I think, I'll have you write down the law, but I think it's kind of messy, the first sentence here. Try to explain this the best I can. All right, so that is our law of detachment. It says if the hypothesis of a true conditional is true. A lot of stuff going on there. Then the conclusion is true. Okay? If the hypothesis of a true conditional is true, then the conclusion is true. I'm going to write a if-then statement here for us. If two angles are a okay. So if I look at this law, it says if the hypothesis of a true conditional is true. If I write that conditional statement down there, the if two angles are a linear pair, then they are supplementary. Would you guys agree that that's a true conditional? Okay, that's a postulate that we talked about, right? That has to be true. So that's in this law, that's addressing this statement here. We've got a true conditional. Okay. Now, in respect to that phrase where it says if the hypothesis of that thing is true, then you can make a conclusion. What we mean there is if I were to close or make you close your eyes, okay, and I tell you in front of you, angle 1 and angle 2 are a linear pair, okay, that is occurring, for that hypothesis is occurring in front of you. It is true in front of you. Does that make sense? Okay. So then you can make a conclusion about those specific angles 1 and 2. If I were to give you, so what happens, I guess, is that when we're looking at this thing here, from that phrase, okay, what they're really saying here is if you have a if-then statement, okay, if you have an if-then statement and the if part is occurring for you with maybe some specific angles, specific rays, segments, whatever, but you have the if part occurring in front of you on your paper or some situation you've come across, that's happening. Then this is the conclusion you can make. Bless you. Okay? And this is the conclusion you can make off of that. I think it makes a lot of sense once if we read that, understand it that way, but then do an example. Okay? So let's see an example of this being used. We'll see a couple of these. And if you guys, I know there's a lot of writing in this PowerPoint. If you run out, if I go a little bit fast, we are kind of on time crunch here, you can go back to the PowerPoint, you can go back to the video and pick up this stuff if you need to. Kind of abbreviate your notes a little bit right now. So here is a true conditional. Okay, I'm going to say if a student gets an A for the final exam, then the student will pass the course. That we've agreed upon being a true conditional statement. Okay. Now I'm going to tell you a second thing. So this is the idea of this is what's happening or occurring in front of you. I had you close your eyes and I tell you this happened. You should be able to hopefully make a conclusion. Okay. This second statement, does that match our hypothesis? Okay. That second statement is saying that the hypothesis of our if-then statement is occurring. It is true right now. Okay. Because would you guys agree? Now it's not word for word, but would you guys agree that Felicia's a student? She got an A, right? Would you agree that a history final exam is a final exam? So that second statement is occurring in front of us. The hypothesis of our if-then statement is occurring right now for us with specifics. Felicia's a specific person, right? Okay. What conclusion then can you make about Felicia? She passed the course. That is, guys, that is the law of detachment. You use it every day. You use it in every action that you ever come across. If it's 3:15, then you get up and go home, right? Here in a little bit, the bell's going to ring. It'll be 3:15. What do? You leave, right? Because 3:15, the bell rings, matches that conditional statement of if it's 3:15, then I leave. Okay? So all your actions that you do every day, every time you think about something, make a decision, make an action, you're using most of the time, the law of detachment. Okay? Now, you don't sit and think, okay, before I get up, am I using the law of detachment or not? You just do it, right? But this class and the things that we're going to talk about right now is getting us to kind of take a step back and start to think and analyze the way we think. Okay? And if we can do that, I think it's going to make a lot of stuff that we go through a little bit easier for us. All right? So let's do this. Let's say that my second statement here was something like this. Let's say we insert that's my second statement. Felicia's 17 years old. Based off of that if-then statement, is there any conclusion I can make about her? No, because that doesn't match the true hypothesis, right? Okay? This idea is not happening in front of us with that phrase. Okay? So I can't make a conclusion. Did she pass? Maybe. But maybe she didn't, right? So I can't narrow in on one concise conclusion. All right? So because they don't match, can't say anything about it, right? Is that okay with everybody? So do another one. Okay, this is more mathematical. Okay? It says if a ray divides an angle into two congruent angles, a ray divides an angle into two congruent angles, then the ray is an angle bisector. That's the definition of an angle bisector. So if it's a definition, it's a true fact, right? Okay? So this is true. Now that second statement, this one right here, says ray RF, okay? Does that, now it's a specific ray, but is it still a ray? Yeah. So this here matches that. It divides. Okay, angle ARB. Is angle ARB on angle? And now it says into two congruent angles. Are these, is that a way for us to say two congruent angles? Okay, so we're seeing that this second statement conceptually matches. Okay, it doesn't have to be word for word. A lot of times it's not because we bring in specific, but conceptually they match. So what can I say then? This conclusion right here is going to be true then. Okay, then the ray is an angle bisector. That's going to be a conclusion that I can make for my specific ray in that second given statement. Is that all right with everybody? So I can say ray RS now is an angle bisector. Okay, the law of detachment. Give you an one that we can't make a conclusion on. Okay, two angles are adjacent and they share a common vertex. Okay, here's my hypothesis. Okay, here's my second statement. Are they the same? No. Okay, adjacency has more criteria than just a common vertex. So they're not word for word same idea here. Okay, so if they don't match, no conclusion. And what does that really tell me? Okay, most people when we look at this, the conclusion we want to make probably most times is that they are adjacent angles, or here they say share a common vertex. Okay, but because this and that do not match, I cannot make this argument about this thing, even though those arguments are the same, aren't they? Okay, but we go back to that, maybe not the greatest example there because those arguments are the same, but it's still nonetheless, they don't match. We can't make a conclusion. It's like saying Felicia is 15 years old, 16 years old, or something like that. We can't, it doesn't match for us to make a conclusion that she's going to pass the class. Yes, that first given, that first if two angles are adjacent and they share a common vertex, that is true. But because they don't match, then there's nothing new that I can gain from that with these two statements. That brings us, guys, into what we call the law of syllogism. Okay, kind of a weird word. Zoom out here, she spell it. Law of syllogism. This is kind of what you guys do on a regular basis as well. Let's say this, okay? If it's 3:15, then the bell is going to ring. If the bell is going to ring, then school is out. So the new statement then is if it's 3:15, then school's out, right? That's a new if-then statement that was created using the first two. Okay? You guys do this kind of stuff all the time. You just don't think about doing it. Okay? It's just something we inherently do. But it says this second law allows you to state a conclusion, state a new idea from two conditional statements in which one hypothesis matches one conclusion. Okay? And we'll do a couple. We got 4 minutes here, guys. We can do all the examples that the rest of the classes have done. You might not have time to write them down, but we can at least talk through them. Here it says, in this example, it says, if it is July, then you're on summer vacation. That is a true if-then statement. Okay, so it's called this statement 1. True if-then statement. There is a second true if-then statement. It says, if you're on summer vacation, then you work at a smoothie shop. Does that make sense? Those are the only 2 statements that I know to be true. But because that right there and that right there, the conclusion of this phrase matches the hypothesis of that phrase, then I can create a new third if-then statement that I know to be absolutely true. And that third if-then statement is taking these 2 things and kind of just deleting the overlap. That's what overlapped, right? And then read what's left over. What's left over? If it is July, then you work at a smoothie shop. That is new information, right? That's a new conclusion. It's a new argument, okay, that we did not start with. And what's awesome about that is that it's true, okay? And that's what we're looking for. We're trying to create new conclusions that are true. This is the part when we get to proofs. I will give you kind of a systematic process that will allow you to solve probably about 90% of every single proof. The last 2 or 3 steps incorporate using the law of syllogism, and that's the hard thing to think about because we got to start piecing things together to create new statements that I didn't start with, but because the statements I used to piece together were true, this new statement is true. Kind of do an example here. Okay, another one. All right, if a figure is a square, then the figure is a rectangle. That's absolutely true, right? If a figure is a rectangle and the figure has 4 sides, absolutely true. Okay? Do we see that this conclusion matches that hypothesis? Okay? So delete those out. Delete those out, and what are you left with? You're left with if a figure is a square, then the figure has 4 sides, right? A new conditional statement that is absolutely true. All right? Look at this one. If you do gymnastics, then you are flexible. If you do ballet, then you're flexible. Okay? Does this conclusion match that hypothesis? No. Okay? Ballet and flexibility, they might intertwine, right? But they're not the exact same idea. Okay? So those don't match up in that order. But that's just one hypothesis and one conclusion. I can also look at that hypothesis. Does it match that conclusion? No. Okay? So because those don't match, and we got to check, when one set doesn't match, you always got to check the other set. When they don't match, there's no third phrase we can make. There's no additional conclusion that can be made from that set of facts. Does that make sense to everybody? Okay? You're going to see, and right now, guys, because it's easy, we don't have a lot of facts yet. We don't have a lot of geometry yet. But if we can get a hang of this stuff with these generic phrases, when we do start learning more geometry facts, it will be easier to piece them together to create a new fact. And then piece those things together to create a new one. And piece those together to create a new one. And keep doing that game throughout the entire year to create these new ideas, new concepts that we use over and over and over again. Okay? I've assigned 2.4. Make that due tomorrow. Okay? 2 to 3, like I said, is also available till tomorrow as well. All right? We're going to spend quite a few days on the next two sections, kind of toying around something, because we're flying through this chapter, which I wanted to do, kind of toying with what we're going to do at the end of it. Okay? We'll talk about that maybe tomorrow or the next day.